when you have your values, it's the value of B that determines whether or not it's growth or decay. So B, if B is greater than 1, growth. Oops. If B is between 1 and 0, it's decay. That's really the only difference between these two, whether or not it ever asks you, is this growth or is this decay? And that's how those everything else gets plotted out the same exact way. Everything else gets going through just by figuring out easy numbers to work with and continue out. When you're dealing with these, you have a parent function, and then you have a shifted function. Your parent is going to be the y equals a b to the x. And when you do that, you're always going to want to just pick the 5 easy. You always want to pick the 5 easy points because then you know where your original points are. And then from there, when you go to shift it, you're just shifting them via the ordered pairs. So this generates your first x to generate your y. And then what I would always do is I always create a secondary table, if you will. And what I mean by that is by adding in whatever your h and k values are. That way you can just adjust all your ordered pairs without having to do work on the graph. It's much, 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 much easier to do it that way. And that's kind of what I was getting at with some of those short videos. I think the one question I had where I had to, was it 3, 2 to the x minus something, and then I had the shift one and I had the regular going. And it was just literally you plot the first one and then you just move the order pairs. Right? And then it was just a matter of just replotting. Your growths, they went up to the right, or they went down to the right. Ha! So you got screwed? So I would fight that, Maggie. Say, take it to the man. So, what's that? Yeah, it's kind of gross outside today. Yeah, as you go through these things, that's kind of what you were looking at being able to do. Could you just pick out some ordered pair parts and go? So, was there one in particular at all you wanted to go through and stuff? I know, Dylan, you were saying you had a question. Do you remember which one it was off the top of your head? Was it a... So let's just pull up we'll do a growth and we'll do a decay. Let's see how we do. So let's see, I think you guys had, let's do 42. Oh, there's a couple little tricks that happen here real quick before I go too far. Yeah. I'm doing the 8.1, the growth one. So real fast, there are a couple of quick tricks. So the parent has a horizontal asymptote at y equals 0. The shift is asymptote is at y equals k. So your horizontal asymptote, the parent function will be at y equals 0. Your shifted asymptote will be at y equals k. Bless you. And that's a nice little trick to remember then, because then you'll understand where everything's being plotted and moved around to. Excuse me. So, going into then on 42, we have y equals 8 times 2 to the x minus 3 minus 3. And just like whenever we have AH and K problems, I always like to label everything. So we have 8, 2, 3, and negative 3. Okay. And from there, it's just a matter of minus points. Growth. So we get our ordered pairs then, just to start out. Let's see, 2 to the negative 2 would be 1/4. 8 divided by 4 is 2. 8 divided by 2 is 4. 8 times 1 is 1, or excuse me, 8, 16, and 32. And that kind of gets us going on that. From there, we just take the H and K's and just add them in. Well, we can do our little rough sketch first. Let's see. Oh. So at negative 2, we were at 2. Negative 1, we were at 4. At 0, we're at 8. And 1, we're way up here, and so on and so on. So we have our parent function. And then when we go to get our shift stuff, it's just a matter now, take our H value was 3, and our K value is negative 3. So I'm going to add 3 to all my x's. Then I'm going to subtract 3 to all the y's. So I have new ordered pairs of, let's see, 1 and negative 1. 2 and 1. 3 and 5. 4, 13. 5 and 29. And just by doing that in the ordered pairs, it's so much easier than trying to look at your grid and count backwards and upwards and all that other stuff. It's so much cleaner to go that way. All right. This is a little trick method that I use with most AH and K problems with shifts, especially when we get to trig. So you're at negative 1, or excuse me, 1 and negative 1, 2 and 1. And then we have to put in our asymptote. There you go. Now, in this case, I don't remember. Sometimes it does ask you to find, I think there was a couple of problems that asked you to find your asymptotes and your intercepts, or your y-intercept. Now, if you're given a problem like this and you have to find out what your y-intercept is, that just means where it's when x is equal to 0. So if you take your value of x equaling 0, it's just a matter of 8 times 2 to the x minus 3 minus 3. Well, what's 2 to the negative 3? 1/8, isn't it? So 8 divided by 8 is 1. So 1 minus 3 is at negative 2. So well, my drawing was bad, but my x-intercept would have been there. And so on. Not x-intercept, I meant y-intercept, excuse me. I'll get it right one of these days. And that's kind of what we're doing. Okay. And once you see it once, it's like, oh, this is pretty easy. Those closed captions were pretty funny. It was great, like, randomized weirdness. Now, if you go to, you were saying number 32 in the decay set, you guys were saying? All right, if we look at that one. Oh, yeah, don't forget, make sure you guys vote for Fontana, not me. Hey, it's funny, I have the, I kissed the cow back to the old All right, so if we're doing 32 from the decay, we're doing 32 with the decay. Remember, 0.75 is 3/4. Might be easier to think of it that way. It's 3/4. You're just going to get some really crummy looking fractions of jump. Okay. So if you go through your setup, you have no shift. All we have to do is get our ordered pairs. -2, -1, 0, 1, and 2. What's that? There's no H and K. So if I substitute through, I'm going to get -5, 3/4 to the -2. Well, that means it's -5 times 16 divided by 9. You flip it and go. Okay. So you do get just, what is that, -80 over 9, so it's not, almost 9-ish. So you get the idea that -80 divided by 9 is just about 9. -9. And then I do the same thing with the -1. So it's -5 times 4 over 3, which gives me -20 over 3, which is only 7. There you go. -5 times 3/4 to the 0 is just -5. Then you get -5 times 3/4, so that's -15 over 4. So was that -45 over 18 over 16? All right. So when you write these things out, guys, it's as long as you get the ordered pairs, and as you're putting them through, that's really all you can do. Right? You get the idea of where things are moving to. So let's see. At -2, we are at almost -9. At -1, we're at almost -7. Zero, -5. It's like Jeopardy. Yes. Okay. What's that? And then it'll die out. So this is one of those. It's going to approach here. Right. That's what it would look like, ish. Thanks. No, and it's a real good question, Sarah. A lot of times when we do, when I do tests or quizzes with this stuff, I usually don't even I don't even have you guys graph it. I have you give me ordered pairs. Because can you identify the stuff out of it without using your calculator? You can do this without a calculator. We got to work on those then. Okay. But really, as it gets into some of these things, the fractions that we use are pretty. They really are. Now, when you get into the last little bit, if you're looking at any of the other ones with the H's and the K's, you're still doing the exact same thing. You still plot the parent function, you plot the parent asymptote, and then you shift it by adding or subtracting your h and your k to each of the ordered pairs. And if you stick with the idea of constantly using -2, -1, 0, 1, and 2 as your start, it's so much easier. Okay? It takes a lot of the guesswork out of everything. Okay? Button that out, make sure you get everything cleaned up. I'll take this tomorrow, but I do want to talk a little bit about letter, their number E. No, I'll collect this. I'll get it tomorrow. Yeah, all like the past 2 days with the junk. So then that way, if you didn't have the graphs clear out, hopefully that'll help you get some of those ordered pairs set up. But when we do the number E stuff, it's the exact same thing, which is something a little slightly off. It's Euler. It's pronounced Euler. Oh, really? So just because of things and stuff, it's not good for you. Anyway. Oh. So what happens here is there's this, and there's the, we haven't shown this formula yet, but don't write this out, but there's a compounding interest problems where you have a specific rate over a specific time. As the number of times something compounds approaches infinity, it approximates to this value. And that's where this Euler's number came up. This at 2.7 something or another, whatever. But what we use with this, this is from basically, this is derived from exponential growth or exponential decay. But the idea behind it is that it's an approximation that occurs naturally in math. And that's where this one comes from. So what we do here is we use this natural, it's called natural base E. And again, I'm not worrying about where this formula comes from yet, but the idea that we do is that we can use this value of E, and we can treat it, whether it's like a variable, we can treat it like it's 3 squared, you know, if it's 3 squared times 3 to the 4th, what would you get? 3 to the 3 plus 4 is, yeah. Oh, did I say 3 squared? I'm sorry. I thought I said 3 to the e to the. No, you were right. You're right. So you treat this exactly like you would. Yeah. So e to the 4th times e to the 3rd is how much? There you go. I'd say that was e. See? I got nothing. 10e to the 3rd over 5e squared is? Okay. 3e to the negative 4x squared. Your exponent rules. Remember, treat this like you would anything else. Excuse me. When you write out your stuff in terms of exponent rules and things like that, what you always want to do is just kind of keep everything balanced. You're still when you use your power rule. When you use your power rule, remember, you're not squaring that exponent. What are you doing to it? Right. So you get 3 squared e to the negative 4x times 2. And that's usually where people will mess up because they're like, oh, it's got an exponent. I should put a square to it. No. Power to power, you multiply. So this is where you see a couple things here. You get 9 over e to the 8x. And then you'd be done. So you still move things around when they're negative and so on. But the biggest catch here is that even though there's a variable with that or negative 4x. Since that's an exponent, you're just multiplying the power product. Yes, sir? Kind of. Kind of. But remember, that value of e has a numerical. It's like pi. Think of like a pretty much. Just like if I had this as pi. If I had that, what would it be? Yeah, it's the same thing. So, the point is that when you have this value of 1 plus r to the n as n approaches infinity, it approximates to this value of e. That's all it means. Same thing. Don't write any of that down. Write this down. Growth and decay. What happens here is that we still treat the e to the x graphically, kind of similarly to what we did with growth and decay, but it's actually even easier because there's really only going to be 2 ordered pairs or 2 values that will make it clean. Everything else is always going to be, guys, everything else is always going to be a crappy number. We don't like those numbers. So we have this idea of y equals a times e to the rx. Well, e is our base. E is always, in this case, will be our value of b, whereas yesterday it was 3 times 2 to the x. Now it's 3 times e to the x, and so on. This value of r is generally going to be written out in either a decimal or a fraction. If it is greater than 0, it's a growth. If it's less than 0, it is decay. A lot of times I've seen questions, is this growth or decay? You would say growth or decay just by looking at the value of r. That's kind of what you're looking at. Notice, and just real quick in the graphs, they're only using 0 and 1 for values of x, because it's really all you can do, because you know kind of very, very little about this. So when we go to graph these, so if I use y equals 2e to the 0.75x, is that a growth or a decay? Decay, because the r value is less than 1. Wait, oh, did I see? I'm sorry, my dog died. So it's greater than 0. I'm sorry, I had to throw it in there. She did. That's why I was gone yesterday. So our value of r is greater than 0. I'm sorry. I didn't mean to say that, guys. That was me. I'm sorry. So it's going to be a growth 1. So the only thing that I can do here, quite literally, is I know exactly where my y-intercept is. Where is it? 2. It's when x is 0. The only thing I really know is that it's going to be at when x is equal at 0. There's my y-intercept, because the y-intercept is when and that's where we're getting at. From there, we still have that horizontal asymptote. We'll be at 0. And its growth means it's just going, it's really all it's doing. You can put, if you put the value of 1 in, then you'd still have to have a calculator to be able to figure out what e to the 1 is, or e to the 0.75, excuse me. I don't want to do that. I know it's a growth problem, and I know it looks like that. Ish. That's why I figured by throwing a couple of these in there today, that way it gives you time to fix any of the growth decay problems. This is a pretty easy one to mess with, relatively short. And then that will give us time tomorrow and Thursday to do the word problems. So which means we won't have time this week to do the quiz, which is fine. So no, not after a long weekend. That's awful. We'll probably have to do it once, but I try not to. So here's the other one. What do you think H and K do here? Same thing, yep. So you have your A value, in this case is 1. Our R value is negative 0.5, which means it's decay. Our H value is 2, K value is 1. When you have your H and K with these, we treat it the exact same way as you would earlier. Unfortunately, this is one of those types of things that you can really only get one clean value as you go through. If I choose my parent function would be e to the negative 0.5 x is a parent. That gives you your 0 asymptote. That's what I mean, parent function. Oh, parent function is the function prior to the shift. It's less the H and the K. We start with that function first and get the ordered pairs, and then we just add and subtract H and K to each of those ordered pairs. That's the easiest way known to man to do all these types of problems. Were you asking something? Yeah. Yep. Growth K, E's. Yep. So we have our parent function there. Obviously, we know that. Excuse me. If I use x equals 0, what's e to the 0? 1. This is decay, which means it's right now, since it is above the asymptote, means it's doing this. Okay. If it was below the asymptote, it'd be coming up to it. Okay. It matches the idea of the same stuff as before, growth and decay. From here, really the only thing I can do is move this point how many to the right? 2, and how many up? 1. Where does my new asymptote go? Very good. Still have a horizontal asymptote at y equals 1. And there's my solid. I don't know if it goes through 2 there. That was just me turning there. I didn't mean it. What's that? Right. So it's just badly drawn. I'm not a very good drawer. So that's kind of why I thought today would be a good idea just to kind of go with this. Because usually I put the graphing with E after I do some of the word problem stuff, but I figured since you guys didn't have a lot of word problem time, or a lot of graphing time with me around, sorry, that way we had time to do that today and go from there. So, you okay with graphing-ish? Let me give you 2 of these then this evening. I didn't have much out of this because most of this goes into the and when I say word problems about this stuff, guys, I mean it's really, really easy. Like, these are the easiest ones we do all year, okay? It's like you have $100 invested at 7% compounding continuously. You have a formula to look at, and you plug and chug. All right, you can answer your question. Ask a question. What do you got? The same nomenclature we had before. Why not? Why not? I'll tell you right now. All right, All right, so let's see, B18. All right, let's rewrite this off the side here. Five fours. Yeah, that's good. So what we'll do is this. I have to put it up there. So this is 8-3. I'm not sure what the page number is. Give me a second here. We're going to go 18 through 32. Every other even means by fours. And then we'll go 50 to 60 even. And then 70, 72. Now, when you're doing the graphs on those, when you're doing the graphs on 70, 72, 74, all you really can graph is the 1 point, and then shift it. That's all you were able to do with an E graph, but you still have to ask for those. I have to put the PDF file in there, so it is, this starts on page 483. I'll have it posted here in a second.